Question number 1. The coefficient of correlation is independent of. The options are only scale, only origin, both scale and origin, and neither scale nor origin. Now suppose you have data like this, and you are trying to calculate the correlation coefficient. Then what it says is, if you have got xi, yi data, you can transform the data by shifting the origin to some other point, let us say a comma b. So you derive new data from this data by these formulas. H and k are called the scaling factors. Then you will a dash, b dash, and then what we will find is the coefficient of correlation without changing the scale or origin, and after changing the scale and origin are both one and the same. So let me make it more clear. Suppose we have decided to use this as the new origin. Scaling we are doing. So naturally this data in the new dimensions will look somewhat different, even though the linearity will not be lost. So each of these data points have been derived from these data points using these formulas. So what the theory says is, the coefficient of correlation in the original dimensions will be exactly equal to the coefficient of correlation in the new dimensions. That means the formula by which you calculate the correlation coefficient in the old coordinates will be the same as in the new coordinates, but the only thing is the data points would have become sufficiently simpler. So you will find that there is no h and k, a and b presence in the new formula. That is what we mean by saying that the coefficient of correlation is independent of change of origin and scale. But if you compare this with arithmetic mean or standard deviation, you will find two important things. Arithmetic mean is sensitive to change of origin and scale, whereas variance is independent of origin but not of scale. But correlation coefficient is independent of both. So the correct option for this problem is C. Question number 2. Coefficient of determination is related to the coefficient of correlation as option A, square root of rho, 1 by square root of rho, rho square and rho. So if you assume coefficient of determination as capital R, coefficient of correlation as rho, then the coefficient of determination is square of the correlation coefficient. Clearly, the coefficient of determination lies between 0 and 1. It cannot be negative. Option C is correct, and as I told you earlier, it is a very important tool to know the strength of the relation between x and y. If both x and y are positively correlated with a high determination value, or whether x and y are negatively correlated with a high determination value, then we say that the relation is between them is very, very strong. Question number 3. From 10 pairs of observations for two variables x and y, the following data is obtained. N is equal to 10, summation x is equal to 66, summation y is equal to 69, summation x square is 476, summation y square is 521, summation xy is 485. The coefficient of correlation is. Now this is a straightforward problem. Remember, this requires a calculator, but the authorities are now not actually allowing students to carry a calculator, but you have got a virtual calculator on the monitor. So given that facility, this becomes a numerical problem. As discussed earlier, you can employ the formula summation xy minus n x bar y bar by square root of summation x square minus n x bar square into summation y square minus n y bar square. N is 10, that is the number of pairs of observations. So all that you need is x bar and y bar. X bar is the average value of the x. This is 66 by 10 or 6.6. Y bar is summation y by n, that is 69 divided by 10, that is 6.9. So insert these values into this and you will have to compute 485 minus 10 into 6.6 into 6.9 by square root of 476 minus 10 into 6.6 whole square into square root of 521 minus 10 into 6.9 squared. So you can estimate and you will get an approximate value 0.69. So simple thing to be done. Option B is the correct answer for this problem. Question number 4. The least square regression lines of y on x and x on y are respectively y is equal to 1.913 plus 1.478x and x is equal to 0.607y. The coefficient of correlation is. Now here we have got the two lines of regression. It is very conveniently given that this is the y on x line and this is the x on y line. However, it is better we make some observations. This coefficient stands for byx. So this becomes the coefficient bxy. These are the two regression coefficients. Observe that both of them are positive. When both the regression coefficients are positive, the correlation coefficient also has to be positive. So we know the property r square is equal to byx into bxy. So r is equal to plus or minus square root of byx into bxy. In this case, there is no confusion that r should be the positive square root only, 1.478 into 0.67, and this is approximately equal to 0.95. Positive because both the coefficients are positive. So B is the correct option for this problem. Question number 5. The formula to find coefficient of correlation R given the variances sigma x squared, sigma y squared and the covariance sigma square x minus y is option A, R is equal to variance of x plus variance of y by the covariance between x and y. B, R is equal to variance x plus variance y plus standard deviation of x into standard deviation of y by the covariance. C, R is equal to variance of x plus variance of y minus covariance between x and y divided by the standard deviation of x into standard deviation y. D, R is equal to variance x plus variance y minus covariance between x and y divided by 2 standard deviation of x into standard deviation of y. Now suppose x and y are random variables having certain correlation. We can compute variance of x, we can compute variance of y, we can also compute what is known as covariance between x and y. The covariance between x and y is a quantity which measures the amount of association between x and y. It can be positive or negative depending upon the nature of the relationship. We have a very important theorem which says correlation coefficient is equal to variance of x plus variance of y minus the covariance between x and y divided by 2 standard deviation of x into standard deviation of y. This can be derived using the theory of correlation, and it can be proved that whenever the covariance between the variables is 0, then the formula gets reduced to this itself. And what is very important to understand is that the dimension of this right hand side, you don't have dimension, it's a dimensionless quantity. So there are no units for correlation coefficient. So this you can find in option D. It's a very important relationship to find correlation coefficient given standard deviations and the covariance. Question number 6. In a certain correlation analysis, the following data is available. Variance of x is equal to 3, variance of y is 2.45, and the correlation coefficient R is equal to 0.55. What is the estimate of the covariance between x and y? So we already know that R is computed from variance of x plus variance of y minus covariance between x and y divided by twice standard deviation of x into standard deviation of y. Now what is all that we know? We know R, we know the variance, which means we already know the standard deviations from which we can estimate this one. So let's write that formula. Covariance between x and y is equal to variance of x plus variance of y minus 2r into standard deviation of x into standard deviation of y. So you need to just substitute the values, that is 3 plus 2.45 minus 2 times 0.55 into square root of 3 into square root of 2.45. So you will be able to estimate this particular value, approximately 2.5, which you will find in option C. Question number 7. If a1x plus b1y plus c1 is equal to 0 and a2x plus b2y plus c2 is equal to 0, represent regression lines of x on y and y on x respectively, the condition is, we have 4 options. Option A, a1 b1 less than or equal to a2 b2. Option B, a1 b2 less than or equal to a2 b1. Option C, a2 b1 less than or equal to a1 b2. And option D, a1 b1 greater than or equal to a2 b2. Now let's look at these things. This is given as x on y line, and this is y on x line. So if you write this equation as x is equal to minus b1 by a1 x minus c1 by a1, then this quantity stands for the regression coefficient bxy. Similarly, the second equation can be written as y is equal to minus a2 by b2 x. Here there is a small correction, x in terms of y, and there y in terms of x, minus a2 by b2x minus c2 by b2. So this quantity stands for byx rather, and we know that r square is equal to bxy into byx. and we know this quantity has to be less than or equal to 1. So if you substitute this into this should be less than or equal to 1. That means minus b1 by a1 multiplied with minus a2 by b2 should be less than or equal to 1. So you will get a2 b1 by a1 b2 less than or equal to 1, or a2 b1 should be less than or equal to a1 b2. You will find this in option C. On the other hand, if the order is reversed, the condition will slightly vary.